This lesson is going to continue on with the subject of net change that we did in a previous lesson, so make sure you have this note sheet. We'll be working on the last page of it, this old AP problem, and we're going to look at rates and integrating them in a different way. So here is a scenario that may look very familiar to you. Let's say you're out shoveling snow and you're doing it in the middle of a snowstorm. So you are shoveling, and the rate that you're shoveling you can think of as a rate out, meaning you're trying to maybe clear your driveway and you're shoveling the snow out at a rate of, oh, I don't know, X number of inches per hour, something like that. But it's still snowing, so I don't know how wise that is of you to be doing that, filling your driveway as well. You've got a rate that the snow is falling or coming into your driveway, so we look at that as a rate in. And you may want to figure out how much snow is on your driveway at any given point in time, given that you're shoveling it out and it's coming in, and you can balance those two rates out somehow using integrals to figure out the accumulation. So the example we're going to look at from the notes is an old AP problem. Sorry for the blurry. I'm going to try to make this as best as I can. In this example, we have a tide removing sand from a beach, which happens as the water comes in and out, it pulls the sand away. And the rate that the tide removes the sand is given by the function r. So this is a removal of sand. And so you're going to think of this, since it's at a rate here, it tells me that this is a rate that something is coming or going out, the sand in this case. A pumping station is on the beach, and the pumping station is bringing sand in. I've never lived by a beach, so I didn't know this was a thing, but apparently it is. So this adding of the sand to the beach is given by a rate modeled by this function s. So this function is a rate in function as it brings sand into the beach. Both of the functions have units given in cubic yards per hour. So if I evaluate anything on this function, I'm going to be getting cubic yards per hour for both of them. So the rate that the sand is being pulled off of the beach is given in cubic yards per hour, and the rate that the sand is pumped into the beach is cubic yards per hour. Those both are rates given as the units over time, so that makes some sense to me. And some further information is our time interval. This is for time running from hours, from 0 to 6 hours. And then they mention that at time 0, the beach has 2,500 cubic yards of sand on it. That is obviously changing as the sand is pulled in and pumped, or pulled out and pumped in also. So let's go for the questions. I've kind of rewritten the information here so that we can see it a little bit better. And let's look at part A. They ask us how much sand will the tide remove during this 6-hour period, and we're going to indicate units. So we're looking for how much is being taken out by the tide. We know that, but we want the total amount being pulled off, and that means we're going to integrate our rate. So this is going to be solved by setting up a definite integral, and the 6-hour period of time is the indicated 0 to 6 hours. Those will be our limits of integration. And we're going to take the definite integral of r of t dt, since r of t models the rate that we're removing the sand. Now that's all you have to write for the AP exam. They've already defined what that is, any more than that, but this was a calculator active problem. And so that integral will be found here. Now you're going to be answering further questions, so on this I would recommend that you go into your calculator and enter r of t as y1, which I'm going to do now. I know this is blurry on the screen there, but you can enter that in your calculator. Pause the video and get that entered. And while you're there, why don't you enter y2 and let that be s of t. So 15. Okay, let me double check and make sure I have those entered correctly, which I think I am good. You can see that, I hope. Okay, so I've got R1, or R in Y1 and S in Y2. All right, now I'm just going to jump to the home screen and clear out this, and let me do my integral that I've got set up here, and that's just going to be integral, math 9, of limits of integration from 0 to 6 of R of t, which I had in Y1. So I'll just put Y1 in there, and that integral is rounded 31.81. I'm going to call it 816. And units are important, even if they hadn't told me to indicate units. If I can, I'm going to. So let's look at the units here. Now, keep in mind the units for R of t, those units were already given to us. Those were cubic yards per hour. dt is also a unit number. It is the change in t, the little minuscule change in time, which has units of hours. So we're taking cubic yards per hour times hours. And the analysis on that means that this answer will be cubic yards, as those hours just cancel out. So that makes some sense. That's the amount of sand that the tide has removed over the 6-hour period of time, and it should be a unit of volume, it's cubic yards of sand. Okay, moving on to part B, they ask us in part B to write an expression for y of t. Now this is a new function, and it's defined to be the total number of cubic yards of sand on the beach at time t. So if I want to look at any, I would be using to do that. So let's look at the composition of that function. If I want to get the total amount of sand on the beach, here's my thoughts about that. It would be good to know how much sand I started with. So how much at time 0? And that's our initial amount. Okay, do we know that? Well, yeah, we know that's the 2,500 cubic yards of sand to start. So we started with that. So I'm going to have the amount added to change that total. But the tide is pulling sand away, so I'm going to need to subtract the amount removed. So there's my thoughts. If I know how much I started with, I add in what was contributed by the pumping station and take out what was taken away by the tide. So each of those has its own part. So y of t, for the total amount, is going to be the amount at time 0. That was 2,500 cubic yards. The amount added is going to be an integral. The integral from 0 to 6 of the rate it was added in. And that rate was s of t, the rate in. Then I'm going to take away the total amount that was removed by the tide. That's another integral of the rate that it was removed. So the integral from 0 to 6 of r of t dt. And that's the calculation I need. They want that expression written down, so here's my expression. And they don't actually ask me to evaluate it. Now, I'm looking at this and I realize I'll need to go back and fix this. It didn't ask me for the amount of cubic yards of sand on the beach at time 6, which is what I actually have written here, because I've let the time run all the way from time 0 to time 6. They asked for the amount at any time t. So that means I need to make a pretty big change actually. Instead of 6 here, it needs to be t. So that could be time 5, time 1, whatever we want, from 0 to any time t. The same change needs to be made right here. This needs to be a variable, limit of integration, making this whole thing an accumulation function. And that also means that I need to change my variables here. Since the true variable of the function is this limit, these need to become dummy variables. So I'm going to change these to just x's. Okay, now, for good measure, I'm going to rewrite that. Actually, I probably on an AP test would want to cross that off and write it again, because I don't want them actually grading that mess. So I'm going to say 2,500 plus the integral from 0 to any time of the amount added, or sorry, not the amount, but the rate that the amount was added, which when we integrate the rate, that gives us the total amount added. And then I'm going to subtract the rate that it was removed in the integral. X, dummy variables, those will trip you up, and I did over here too. Ah! All right, I think that's clear enough. So there's the answer to part B. Be careful about those. Okay, part C. We're going to find a rate at which the total amount of sand on the beach is changing at time t equals 4. So the rate at which the total amount of sand is changing is going to be the derivative of the total amount of sand. In part B, we wrote an expression for the total amount of sand altogether, which was y of t. So now if we want the rate that it's changing, we need to take the derivative of y of t. Okay, so let me remind you, let's maybe layer these. This is y of t in terms of accumulation functions, and we want to take the derivative of this. So one term at a time. The derivative, of course, of 2,500 is 0. Moving to this term, the derivative of this accumulation function is fundamental theorem of calculus. If I'm taking the derivative of an integral, I plug that upper limit of integration into my function and then multiply by chain rule and I'm good. So that's just going to mean s of t. The upper limit is the evaluation variable on this function in the integrand. S of t minus, same thing here, we're going to just say minus r of t. Okay, so that should make some sense. Conceptually, here's what we're saying. This stands for the rate that the amount of sand is changing. That's the total amount. The rate that the total amount is changing. Not spelling changing well. The rate the total amount of changing is equal to, remember, S of t is the rate that it was being added in, and R of t is the rate that it was being removed or taken out. So that makes sense to me. If I take the rate it's coming in and subtract the rate it's moving out, then that gives me an overall rate of change. That makes some sense to me. So they want to know specifically at time 4. So we will just evaluate this function, y prime at 4, by doing s at 4 minus r at 4. So let's go ahead in our home screen and evaluate both of those. All right, so s was my y2 function, y2 at 4 is this decimal 4.615. And then let me do R, which was my Y1 function, also at 4. Messed up there. Let me try that again. Also at 4. Okay, Y2 at 4 is, all right, let me try that again. I already did Y2 at 4. This is crazy. Y1 at 4, 6.524. So I'm just going to jot that information down. S was 4.61 ... minus 6.524 ... We're going to subtract those. So the difference between those two, I am not doing calculator stuff well here. I'm just trying to subtract these. It's not that hard, Mrs. Pryor. Okay, I got it. So this is a negative value, obviously, negative 1.9087 ... All right, so if the sand is being added in at a rate of 4.61 and some change cubic yards per hour, and taken out at this higher rate, 6.5 cubic yards per hour, you can see that the rate of change in the total amount of sand is negative. So the amount of sand in the beach is decreasing at this rate at 1.908 cubic yards per hour. They didn't ask me to interpret that, but that's the interpretation. The rate of change of the sand on the beach is negative 1.09 cubic yards per hour. That means that the sand on the beach is decreasing at this rate. All right, we go to our last one, part D. Over our time interval from 0 to 6, what time is the amount of sand on the beach a minimum? So do we have a function for amount of sand on the beach? We do. That is y of t. And they want us to figure out when it is a minimum. So we are going to do a candidates test. This is a candidates test problem, looking for the absolute minimum value. So that means I need the derivative of y of t. So y of t, we just figured out the derivative in the last problem is s at t minus r at t. Y prime of t, I think I misspoke there. Y prime at t is this. And we need to set this equal to 0 in order to find our candidates. And that means that we are looking for where s at t is equal to r at t. Do you remember how to solve something like that? I don't think you're going to be doing that by hand. Where do these two things equal each other? This is going to be, let's put these graphs in the calculator and just find their intersection. Okay, so this is a chance to walk through that process if you can see it. Okay, your goes, use the x min and max that were given in the interval of time. X min and max should be 0, 6, and I don't really know what the y min and max are going to be, so I'm just going to leave them at 10s and see what happens. Let me hit graph and see what we're looking at. So here we have a graph of r of t. That doesn't look bad. And then we have a graph of s at t. And it looks like we have an intersection point here, and there may possibly be one right here. I don't know for sure. So I'm going to more towards the origin. So for calculating that intersection, let me do second trace and choose my intersect number 5 choice. Enter for the first curve, enter for the second curve, and enter for the guess. And it is taking me to here. So if you got the same thing I've got, my intersection is reading off at 5.11786 and some change. Okay, so let's take a minute to jot that down. Now, before you do anything else, I want to store it. What you need to do is do a second quit right here and exit back to the home screen. Then just hit store, because the last answer you had was that intersection number. And I'm going to store this as A. My value is going to be A. Oops. Alpha A. Okay, there it is, the 5.11786. There, it's stored there. I'm also going to write a note to anybody reading my paper that this is going to equal A, and if I use this number anywhere else, I'll just represent it with the A. So let's go back now, and let's see if we can find an intersection on that graph over in this area. So I'm back to the graph, and I'm going to zoom into this little section with a box. Hitting the zoom button, number 1 choice is box. So I'm going to use the arrow keys and arrow my little guy, my little spider guy, over to that region, and hit enter to mark the corner of a box. Then using the arrows again, I'm going to build that box down and over and hit enter when the box is where I want it to be for that little region right there. Let's see if this is going to give us another intersection. I'm going to call it a no. So that means that I'm looking at just the one candidate. that comes from critical numbers. I've just got this one critical number, but candidates also include the endpoints, keep in mind. So I'm going to make a table of values here to list my candidates. My candidates are my critical number, 5.178, or I could just put A there. Maybe that's what I should have done. And then the endpoints. The endpoints of the interval are 0 and 6. So it just is, let's figure out what the amount there is. Let me label this as a T and this is Y at T. Okay, so figuring out Y at my critical number, we'll use A here. Y at that critical number. You'll see the beauty of storing that number in here. So in the calculator, I'm going to go to my home screen. Oh, before we do that, let's write it on paper. What we're going to do for Y at A is go back to part B where we had our function for Y right here. And we're going to just plug A in for our time. So 20 of S of T, S of X, you can use whatever variable you want. I'll go ahead and use X. dx minus, same integral from 0 to A, this time of R of X dx. Okay, so just remind you, 2,500 is what we started with. We're accumulating an amount of sand being added in, so we integrate the rate that it's added in from 0 to our time, and then we take out the integral of the rate it was being pulled out from 0 to our same time. Okay, so that's going to go in a calculator. I'm going to do it all at once. I'm going to go with the 2,500 plus math 9 for the integral from 0 to A. Okay, and storing that value, I'll just say now, is the only way to get the accuracy to 3 decimals that you're required to get. So going from 0 to A of S, and that was in my Y2. So my Y2 there, dx. And then the next part is subtract another integral from 0 to A, this time of R, which is stored in the calculator as Y1. Okay, doing its thing. So we have 2,492.369 and some change cubic yards of sand at time A. Maybe I'll add that to my table over here. Okay, so that's our only candidate as far as critical points goes. The other candidates, we have 2 more candidates on like 0 and 6. So Y at 0, that one's a little easier than you might think at first. We're not going to have to do this again because this was our given initial value. They told us right out at the beginning that the amount of sand at time 0 in the stem is 2,500 yards. So we don't have to do anything else. Just make a note of that. We do need to figure out Y at 6. How much sand is on the beach at time 6? Okay, so for that calculation, I am going to just do this in my calculator again. I'm just going to go and do an edit of the first one I did. Let me arrow up and hit enter so I can edit this line. All I need to do really is just change the A to the times 6. And I need to do that in both places on my integral. Okay, so at times 6, we can get our calculation 2493.276. Let's write that down. I guess that would round to 7 if you want to round it. Okay, so let's answer the question. When is the amount of sand on the beach a minimum, and what is that minimum value? And we've justified it. Our answer is the lowest one of these, which it looks like it's right here. It's at the critical number. And so for my final answer, I'm going to write that in a complete sentence. I'm going to just simply say the amount of sand on the beach is a minimum at T equals 5.117 or 8. You can give either one. Is this hours, seconds? Hours. Look back up. Hours. Units on that. And the minimum value, they did ask for both, so I'm going to make a new sentence here. The minimum value, how do you spell minimum? The minimum amount, actually, instead of value. The minimum amount is 2,492.369 cubic yards of sand. Okay, and there you have it. Now, I am going to post on Canvas probably an answer key to this. Remember, this was an AP exam question, so I'll put up the rubric and you can compare the rubric to the work that you just saw here. And I hope this goes well. Remember, rate in, rate out. If you integrate the rate, you're getting a total amount. And so have a good one, get some practice in.